So, like he said, I'm going to be talking about trust and verification of Git commits and signatures. So, the problem I want to explore with you today is how to attest to both the changes and the state of the repositories that we work with every day, both as maintainers and as end users. And I'll start with going over a little bit the motivation and the motivation for doing this kind of work and what it actually brings to the table. Then I'll discuss the solutions and some of the practical problems associated with signatures and signature verification. Then we'll go over how to actually sign and verify work with Git and end on some workflow considerations. Now, the problem we are essentially addressing is one of supply chain integrity. Is the repository that I'm working with the genuine article, and how can I actually attest to that? And for those purposes, we have a number of different things in Git. We can verify the individual commits, we can verify merges, tags, or releases, or even pushes to remotes. The solution that we are looking for are digital signatures, or signatures for short. And like many things in IT, dates back to the late 70s and so on. Excuse me. Basically, the technology underpinning signatures are a function of some of the cryptographic algorithms, most notably RSA, and today more modern schemes like ECDSA and EDDSA. And they provide a number of properties that we are interested in, most notably authenticity, integrity, and non-repudiation. The way that these schemes work is that they play on public key algorithms, and if we do a little recap of them, public key cryptography or asymmetrical cryptography are algorithms that work on a pair of keys. You have a private key that you keep private and an associated public key that you disseminate to interested parties. The two properties of these algorithms and these systems is that data encrypted with a public key can only be decrypted with the associated private key, and on the other hand, signatures created with a private key can be attested to if you have a faithful copy of the public key. Now, with these two operations and a protocol to decide on the interoperability, if only to decide on, which algorithms we are using, which message digest functions we are using. We need to have something to decide on that so two parties can interoperate. And for that purpose, we turn to OpenPGP. OpenPGP, or Pretty Good Privacy, started out in the early 90s as a tool published by Philip Zimmermann, and was ostensibly used for private and confidential communications. And over time, it grew a lot of features, and the behavior of the tool itself got standardized. I don't remember when, but ended up being codified in an RFC, which defines the supported message formats, the packets, and the methods for computing signatures and verifying them. The most widespread implementation of PGP today is the GNU Privacy Guard, or GPG, which, depending on your outlook, is either a kitchen sink or a veritable Swiss Army knife. It unfortunately has gotten a little bit of a bad reputation over the years, especially in terms of usability. A lot of that is actually intrinsic to PGP, like we will see. There are other implementations possible because you can graft Git almost indefinitely with modules or even in core, as we've seen before here. But it's out of scope for this talk, so we will stick to GPG. Central to PGP and GPG is this idea of a web of trust. And the reason why we need to consider this is that to be able to do any kind of verification operations, we need to have a trust relationship with the party that we are verifying from. For example, the maintainers or producers of software or code that is being signed. And this idea in PGP was to have a completely decentralized way of forming these trust relationships. Essentially, PGP users would meet up physically at key signing parties where they would verify each other's identities and sign each other's public keys, thereby providing a binding between the public key and a real identity. It turns out that this is like the Achilles heel of PGP because this method of scaling both communications and other operations doesn't really work when we start to talk about parties in the number of millions, if not even billions today. However, there is no reason to throw the baby out with the bathwater. In a more constrained operations, like only for code signing, the web of trust, especially coupled with the new trust model, it was introduced, I think, in late 2015 in GPG, a trust model called TOFU, which is essentially trust on first use, something that you might be familiar with from SSHing into new hosts. The SSH client asks you to verify a fingerprint, you say yes, and after that point in time, you kind of trust that fingerprint forever. Exact same principle here. It does provide a much weaker security guarantee, but it can be coupled with PGP and key signing to give you a more robust network, which isn't practically needed because when verifying signatures, we don't have this many-to-many relationship. We only really care that the code we are using is coming from someone we have a relationship with. And it doesn't even need to be a personal relationship. You don't really need to meet the contributors or builders of the code that you use, although that is a really great thing, and probably the reason why we all go to conferences. But nevertheless, it provides a much more practical usage scenario. Now, having dug a little bit of a hole into PGP, I hope you'll humor me in digging a little bit further and touching upon key generations. Now, I could spend a lot of time discussing algorithm choice, like should you be using RSA keys of size 2048, 4096, or should you be using elliptic curve algorithms, which one should you be using, and so on, which is a very fun discussion to have over beers. So let's suffice it to say that the defaults today in GPG are pretty good and will remain pretty secure through the next 10, 15 years. However, there is one thing that I do want to talk about, and that is expiry time. One of the biggest problems we have when maintaining these trust relationship is the fact that if you have a private key and it does get compromised and you have to revoke it, that operation for the people that have a relationship with you is an online operation. They need to be made aware of the revocation. And this sometimes falls through the cracks. So when keys are created with very long expiry times, sometimes in the order of years, decades, or even infinite, these might fall through the cracks. So short expiry times, less than a year, less than 6 months, or even better if you're maintaining a software project, tie the expiry of the key to the long-term support of the release. This also has the added benefit of perhaps motivating people to update. Further, using the same key for everything that you do is just not good practice. You want to have one key for your personal use, one key for each project that you work on. It does add a little bit of overhead, especially in terms of keeping backups of them, keeping those backup saves, or even just remembering or maintaining the passphrases to them. But compartmentalization in security is king. Further, on key hygiene, when you are generating a key, you should ideally try to do this on a machine that is not exposed to the wider internet. By, for example, booting a Linux live CD, which is guaranteed to have the tooling required. Or you can even take it further and using hardware-backed keys, so-called OpenPGP smart cards or USB dongles. Some of them support generating the key on the device, and the device itself may be engineered in such a way that the private key material cannot be physically read out of the device. So all signature operations and everything happens on the device, providing for excellent security, for example, if your workstation gets compromised. An adversary cannot start generating comments and signing them or signing other documents, causing some havoc later on. Further, There are implementation of these devices that require a user presence. So you need to actually physically touch the device to get it to do anything. And you might want to also consider using subkeys. So don't use your master key for signing. The reason there is that the master key is used for all of these maintenance operations, such as signing other people's keys, extending the expiry time, or even generating generating subkeys. I will post at the end of the talk a link to a GitHub repo where I will have both the slides and links to some very, very good resources on how to actually accomplish this, both hardware-backed and without. So I am going to make one huge cop-out and not talk a lot about how to actually manage your public keyring for the project that you're interested in, simply because there is really no single good rule for this. But verifying the fingerprints of them, comparing it to multiple sources, and just keeping an eye on the rotation after either expiry or revocation. It's unfortunately a much harder problem than it ought to be, but as of today, there is no really other way to provide these kind of attestation capabilities that we are interested in. So with these small details out of the way, let's look at signing and actually verifying work with Git. And we'll start with commits as kind of the basic building block of repository history. Now, commits are point-in-time snapshot of the repository that you're working in, not actually the actual changes. And if we take a look at a commit object, we see that it references a tree. So the tree object is basically the thing that encodes both the directory structure and the files in your repository. And it has references to the blobs that contain the actual contents and so on. So along with this header, you have the parent, which is the tree state before your commit. If any, like the root commit on your repositories will not have a parent, along with author and committer metadata. And notice it is always the committer that is making the signature, not actually the author, followed by a blank line and the commit message. Now, if we ask Git to actually create for us a signed commit, we see that it's actually not a work. Git is actually not doing a lot of this work. It's shelling out to GPG to actually do the heavy lifting of creating the signature. Now, if this were actually committing real changes or to some files, creating or removing them, adding directories or so on, what would happen under the hood is that Git records all of these changes and stores them, then it builds the commit object. After having done that, it passes it down to GPG via standard input and simply asks it to create a detached signature of the document, which it emits and Git reads, and then adds it as a new header into the commit object before putting that down to storage. And we can see a commit object that we just created is identical to the previous one with the addition of this single GPG sig header. Now the blob that you're looking at there, the PGP signature, this is the ASCII armor encoding of an OpenPGP signature packet as defined in the RFC. And with a little bit of copy-paste work, we can put it in a file and dump its contents. And like we would expect for something to guarantee interoperability, we have some versioning info to be able to know how to parse the packet. We have the signature type, the algorithm that was chosen to create the signature, along with the message digest. We have the user identity that created the signature and its key, and a few other miscellaneous data there. To verify a commit, it's very, very simple. But again, this presupposes that you have a public keyring containing the public key of whoever made that signature. And for it to actually be valuable for you, you have to have established this kind of trust relationship. Essentially by downloading the public key from a key server and then going around a checklist or whatever, depending on the project, trying to verify the fingerprints. Or if you're lucky, it's someone you know and you can do it in person. But again, it doesn't scale. Now, looking at the verification itself, we see that we can ask Git to actually output the commit that it's asking us to verify. And we see it's the same commit object with the signature removed. So Git has to reconstruct the actual commit object. This is just passed down to GPG that then calculates the signature and emits some output, which Git actually dumps on you completely verbatim. So if you have configuration in GPG to either highlight or call out fingerprints or use longer key IDs and such, this will all be available to you via Git. Further, there's a second type of commits, so-called merges. And I mean, they are basically just like commits. The only real difference is that they record a multiple parent. I would say that signing individual commits does have value, and we will discuss that a little bit later, but merges are a little bit more interesting from the perspective of accepting outside contributions to your project. And there is one thing to keep an eye on there. If you're doing so-called fast-forward merges, where you're simply rebasing the brands on top of yours, Git will not create a merge commit, which means that you cannot really sign the resulting merge in a way that allows your user to attest that this is something that you as a maintainer did. It does maybe then interfere with workflows that prefer having a linear rebased history, but I think it's a valuable trade-off to do that. Further, when doing merges, you can ask Git to verify the signature of all of the commits you're about to merge. And if you decide on doing non-fast-forward merges, you can also, of course, ask it to sign the resulting merge commit. And it's basically the same process of verifying individual commits, followed by the same process of creating the commit signature for the merge commit itself. Moving on, we have tags as well. Git has the concept of two types of tags. There are the lightweight tags, which are just references to other objects in the repository, and they are not stored as first-class Git objects, and therefore cannot be signed. However, annotated tags can be, and they are first-class Git objects. And a little bit more useful, we have kind of, I think, reached the stage now where annotated tag has become synonymous with release, although it can, of course, be used to record any other interesting point in history of your repository. And similarly, if we look at the contents of an unsigned tag, we see that it records the object that it is referencing, its type, along with the tag itself, the name, who tagged it, and the tag message. And moving on from that, just like for commits, it turns out it's the exact same process, which is very understandable because digital signatures work on arbitrary documents, and the difference between tags and commits in terms of that is a zero. There is a little bit of a difference in the way that they are stored. The signature is not stored as an additional header. It is appended to the document. And as far as I could tell from looking at the Git history of Git, this is just a development decision. And realistically, it has no impact on how you do the verification or work with it at all. Similarly, the PGP signature packet here is just the same as for commits. And the verification works pretty much the same. And again, it presupposes the existence of the public key associated with the signature. There is a third thing that you can sign, which unfortunately is not widely deployed, and that's pushes or push certificates in Git parlance. Now, with tags and commits, you can attest to the authenticity and integrity of those two things, but they tell you nothing about where they are supposed to be in the history of a particular branch. So say that I push some branch Y, there is no way for either the remote itself or even later users to know that I wanted a particular commit to be at the tip of that branch. So what push certificates do for us is that they allow us to create a signature packet that we can verify, where we can provide this method for both the administrators of the repository as well as other users that a particular commit was meant to be at the tip of some branch or somewhere in history. Unfortunately, this does require some server support and extra configuration, the biggest one being that you need to share on nonce to prevent replay attacks, which is why you don't see it on the free open source hosting providers. It's a very cool feature, but to be able to talk a little bit about workflow considerations, I'm going to skip over them a bit. So when we decide on sign and verification, it's a good idea to start thinking about who is doing the verification and to what purpose are we actually signing things? And who does this end user really trust? And conversely, when we are doing the verification, do we care about all points in history of the repository, and who do we trust? So if we start again looking at commit first, individual commits making up the history of the repository are very unlikely to be of interest to the user at every single point in time. It's much more likely that they care about your releases. There are also issues associated with it in terms of just development. If you're signing every individual commit, it gets tedious at some point. I have personally probably clocked around an hour staring at a Git commit or a Git rebase operation, not progressing because I forgot to touch my Yubico. And as soon as you get into those kind of situations, a developer will have a very nice incentive to automate this, which effectively means moving the key material to a place that's more easy to compromise. So you kind of devalue maybe the value of the signatures in there. However, merge commits are a little bit more interesting. But in this case, the end user is probably not very interested in the origin of the changes. I mean, from the software perspective, yes, maybe. But in terms of being able to attest to the state at the point of that merge, it's not so likely that your random user cares that the commits came from contributor Alice, contributor Bob, or Charlie, or whoever it is. So in these cases, signing the merges provides a much better value for the end user to be able to kind of know what he is getting. And he probably also doesn't have a trust relationship with the contributors of your project, while he does have a trust relationship with you. So it kind of seems that tags are it. And I kind of believe they are. Releases are, from the user point of view, the most valuable thing. I'm much more likely to be either building from, deploying, or vendoring your point releases rather than whatever is going on in master. It also does have the lowest overhead for contributors, as they don't need to worry about signing or establishing trust relationship and all of these things. And you would kind of hope that during code review, you would catch any malicious activity there. So we kind of don't need to, we can kind of define that problem away. Again, it's also a little bit of a lower overhead for the maintainers. They don't, conversely, have to establish these trust relationships or worry about the signatures there. They just need to make sure that they are signing the merges. Then, again, when it comes to the release time, we can discuss a little bit about what's ideal there, or what I would consider the best thing to do. And being very subjective in this, I do think that incoming contributions should be merged locally, and by locally I mean relative to the key. This is still compatible with most web workflows you have, be it in GitLab, GitHub, Atlassian Stash, and so on, because the merges, the pull requests do get closed at the time you merge the branches. Having the merge signed by the maintainers and having their public keys available in much the same way as we have the public keys for the project, and kind of define that as internal integrity of the project, so it becomes easier to tag the releases. You don't need to do any re-reviews or worry about grafting in the repository. And then, of course, that releases happen early and often, and that the project has a release key. So I only need to establish a trust relationship with one identity per project, not all of the maintainers. and of course that the tags get signed with that. So to end this, if you just sign one thing, sign tags, when you publish your public key, push it to the key servers and make sure to put your fingerprint everywhere. Have somewhere in your repository an easy list of doing cross-checking. Go to Keybase, I have my public key there, I tweeted my key there, I have it on my website, I have it on the project website, even put it in the repository itself. Plan for rotation, because revocation will inevitably happen. And by using short expiry times, you kind of exercise this all of the time. And like I said, the repository there will be uploaded with some further documents and manuals sometime tonight. So that's it. Thank you very much.